poll with you guys because I don't know you, and I assume the composition of the crowd. So who of you has never programmed a GPU before? Woohoo! Wow. Who is working on a daily basis with GPUs? Okay. Well, I guess I have to shift priorities right now, but I think it's going to work out fine. All right. So my name is Peter Steinbach. I'm coming from Dresden, from the Max Planck Institute of Molecular Cell Biology and Genetics. And I'm going to talk about C++ on GPUs done right, question mark. And I don't want to give away any conclusions right now. So a couple of disclaimers. So for the So for those of you who expect an OpenGL or Vulkan talk, this is your chance. Get out. Okay? I don't want to waste your time, guys. Okay? So this is about scientific computing, exploiting the massive parallelism of GPUs for scientific computing. And I thought I'd just bring one because, you know, I'm the kind of guy I like to, know how it feels. And this guy is damn heavy. Back in the day, this is a Tesla Fermi card. Our institute purchased like 2 or 3 years ago. Back then it was 4K euros. So 4,000 euros. And I just want you to, I'll give it around and just put it in your hand, just to feel what it weighs, okay? Okay, because I mean, we're all programmers, we're sitting in front of a terminal or editor all day, and I think it's a nice chance to just, put it in your hand. It's not a gaming GPU or something, so please don't break it. I will put it back in the server when I get back, okay? And also, don't spill any coffee, right? It's supposed to work. All right. Cool. This talk is open source. Everything, slides, code, everything. It's all on GitHub. If you want to take a picture, do it now. I'm going to flash it at the end as well. And I did this for 2 purposes. First of all, because I think open source is nice. Second of all, I want to use this as a discussion hub. So if you guys don't get a chance to talk to me or don't get off your question, just go there, open an issue, and say, hey, Peter, I didn't understand X, Y, Z. Or what were you thinking? Whatever. So feel free just to hop on over and post an issue, and everything is under Creative Commons. If you find any copyright infringement, don't send your lawyers right away, please. Just ask me. I can fix it. Okay? So just as a disclaimer. So who am I? I already stated my name. I'm having the position of a scientific software engineer at my Max Planck Institute in Dresden. A couple of facts about it. We roughly have 450 of staff. And my task is basically that the scientists come to me and say, hey, I wrote a program, but it's slow. Can you do something about it? And I said, let's see. And most of the time it works out, and I can help them. But what I actually want to say with this slide is I'm not part of the committee. I'm a developer, hopefully just like you are. And this is also the scope of the talk, okay? I'm one of you guys. I don't want to tell you something which will be available like in 5 years from now. The talk is laid out so that you go home today and can say, okay, if I need to program a GPU, I know what to use, all right? So that also means I'm going to be honest, okay? I will say clearly what I think didn't work or does not work in practice and what does, all right? So if you are hired by a vendor or employed by some big company called Intel, NVIDIA, or AMD, probably I'm going to say something that your marketing people won't like. But that's a different story. Okay, so what do I do? Like really? So this is a video taken of C. elegans cell under a microscope. The top view, what you see, is the raw imagery that we get. Okay, this is how it comes out of the instrument. The bottom view is the same imagery after a deconvolution algorithm that I was asked to put on the GPU because it was too slow. And I guess I don't need to say anything more about this, that this algorithm does a great job, right? Because you can actually see cells, right? Isn't this great? So I'm basically, as I said, I'm working with scientific algorithms to be ported on GPUs. And for this specific task, which I hope to release early next year, the problem is actually the data size. So the problem, the algorithm itself uses a lot of FFTs and it's iterative, so it's actually suited for the GPU, but the input data is pretty big. But that's a different story. Right, so this is the outline of the talk. First, I'm going to tell you a little bit, or make a short introduction about massively parallel programming. Then I have to apologize, because for the practitioners among you, this will probably be the boring part. I'm urged to actually show or discuss the architecture of GPU chips, because that has implications how you program them. And then we come to the most important part of the talk. I will show or discuss something that you can use today. So you can go home, install the compiler or whatever and the driver, and then you can go. And then really briefly at the end, I will discuss what you can use tomorrow. So meaning in the near or distant future. So massively parallel programming. I just like this picture of Titan. So this is, and that's why I often use it. So this is the Titan supercomputer, number 2 in the top 500, even the recent ones. It's a supercomputer which consists of 18,000, I repeat in words, 18,000 nodes. Each node has 1 GPU in it. So it's 18,000 CPUs plus 18,000 GPUs. And I want to make a point here that basically GPUs are here to stay. I pulled this diagram from the top 500 list. On the x-axis, you see the year. And what basically these colored graphs mean, this is the proportion of supercomputers that actually use accelerators, be it GPUs, so NVIDIA cards, in that sense, AMD cards, or the Intel Xeon Phi accelerator. And the red line is basically using the entire list, and the blue line is just using the top 50 installations. So what does this mean? So guys, remember, these are huge installations. People work like 1 or 2 years to actually do the procurement. They sit down and think, right? And they get money from the government to spend a whole lot of money. And they just go, wow, there's a new trend. And the marketing people say, it's really fast. Let's go for this. No, what they sit down, get a sample, really evaluate it thoroughly, and then they make a purchase. And this is going to run for 3 to 5 years, depends on the installation, and it will be maxed out by users. So if they think that accelerators are something to use, you know, I would say GPUs are here to stay, okay? So this is just what I want to convey with this. So what are your vendor options? Most of you guys probably know this already, basically. So we have NVIDIA on the left-hand side with their Tesla line. Again, similar to the card that is going around. This is a GPU without graphics, so to speak. Then AMD with their Fire Pro series. And then there's the Intel Xeon Phi accelerator. I have another disclaimer right now. I'm not going to talk about this today, okay? Just so you get an impression what the capabilities of these cards are. So on the left-hand side, basically the model that is pretty much installed in a lot of installations today, which is the NVIDIA Tesla K80. It's basically 2 GPUs glued back to back of each other. So you get 2 GPUs in the hardware of 1. And the total system, or one of these K80s, has the capability of giving you 8.7 teraflops single precision, okay? Then the contender or competitor AMD, this is a fairly recent model, is not used so widespread as NVIDIA, comes with a little bit more memory and also higher bandwidth. And take note, this is a single GPU, which can give you 5.2 teraflops. And then the Xeon Phi, totally different architecture, less memory, similar bandwidth, and gives you only 2 teraflops per teraflops, yes. To give you an impression about the pricing that I'm talking about, 5.5 thousand euros, 4,000 euros, 2.2. Okay, just so you get a feeling. Because, you know, it's always like a data center purchase them and then you can use them. So it's just like, oh, I'm using a GPU. But for me, it's always important to have the relation. So what does it mean? All right, now comes the architecture part. Okay, so this is a picture of the NVIDIA KEPLER chip under an electron microscope. And this is a view of my workstation. I like my workstation. And that's why I thought, I'll just share it with you. So what you can see, there's the CPU. Actually, there's another one. And down at the bottom, there's my K20 that was kindly donated by NVIDIA. to a GPU Excellence Center at the TU Dresden that we are part of. Now, what I want to show you really early on is 2 white boxes, not 1, 2, right? 2 white boxes, which means that if you want to go from here to here, you have to go through the motherboard, the PCI Express bus, then you land here. Very important. And this is often something the vendors want you to forget, okay? But it's something very distinct, which might go away in the near future. I don't know. We will see. But right now, this is the state of the art. And a server basically looks the same, just flat to you and yeah, somewhere in a dark room. So if you look at the architecture of CPUs and GPUs, I thought, so the idea behind how can I convey it to you? And I think this is a quite fitting metaphor from nature. So if you look at 2 kinds of fish, for example, here, a kind of tuna. So the tuna is a predator. It lives in like hordes, but in principle, it's a single individual, right? And it's pretty darn fast. I mean, yeah. And it has a couple of pretty sharp teeth and very versatile. On the other hand, if you look at forage fish, individually very small, there are very many, not very capable, right? But what they, for example, do, I don't know if you guys know this, that when they are in their forage fish school, the wake field of one fish is exploited by the neighboring 2 to actually suck in or accumulate food. And this is an almost one-to-one mapping to CPUs versus GPUs. The CPU is very fast, right? Well, sorry about this. Very fast and very versatile, whereas the GPU has its distinct properties, but its layout for massive parallelism, okay? So for the following 2 to 3 slides, I will use the NVIDIA KEPLER architecture, but in principle, the setup or the concepts are the very same on AMD hardware. Well, not very same, almost the same. All right, so this is how it looks roughly in a sketch. So let's say on the left-hand side, you have CPU land. Somewhere there's memory. And if you want to send a program or execute a program on a GPU, you have to communicate today via the PCI Express. And then your program and the data tentatively lands in the device memory. And then there's a memory hierarchy until it actually lands on the components on the GPU that really do the work. On NVIDIA architectures, these are streaming multiprocessors, in short SMXs. And for example, on the K40, which is half of the K80, you have 15 of these, okay? So this is what is on one die, right? So this is one die up here, this row. And right. So if you zoom in on one of these streaming units, you basically have the functional portions, so that actually do the arithmetics and the logical operations. On NVIDIA hardware, they are called CUDA cores. In the KEPLER architecture, you have 192 per streaming multiprocessor. They are then using a pretty decent register file of 64 kilobytes. And then attached to this is another small hierarchy of different portions of memory. You don't need to memorize these. I just want to say that each individual portion of attached memory has its distinct purpose. So, well, level 1 cache is level 1 cache. One thing I would like to point out is this. This is shared memory, which is there to synchronize and communicate between individual threads. Okay, and there are other memory portions that might be useful to your program. One thing to keep in mind: one of these streaming multiprocessors, if I understood the NVIDIA documentation correctly, can execute 192 floating point, single precision floating point operations per clock tick. Okay, and we're talking about 900 to 1,000 megahertz. Okay, so the basic principle behind GPUs is the principle of single instruction, multiple threads, right? So if you just look at the single thread level, you will be disappointed because there is no single thread. the smallest unit of concurrency on GPUs, especially here on NVIDIA hardware, it's 32 threads. Take note, 32 threads, a lot, okay? Each of those individual threads, which you as a programmer hardly have any control over, is executed on a single CUDA core, and all threads execute the same program, just as the paradigm says. Now, let's go up a little bit. We will slowly close in on the programming. These sets of 32 threads, which are in NVIDIA speak called warps, can be grouped into blocks. Blocks contain a number of warps. The threads inside, or warps inside, can synchronize between each other, so they are barrier constructs. They can exchange data through the memory compartments that I just showed, etc., etc. And then, because life is not easy, and so is programming for GPUs, of course, a bundle of blocks is called a grid. And basically, this whole construct is meant there to serve as a work distribution mechanism, okay? And these individual, so basically when you launch a GPU job, the entire grid is dispatched to the entire GPU. Blocks are selected that are dispatched to the streaming units, and then the streaming unit decides which warps are actually executed and when, okay? Now, that's all nice, but of course there are problems, architectural problems. So on the KEPLER architecture, if one of your threads or warps wants to access this device memory, it takes it roughly 200 to 400 ticks. Now, an actual floating point operation can go much, much faster. So what actually the architecture has to do is hide this latency somehow. So imagine you have a warp that needs to do some work. So it will be dispatched to the streaming unit, and once it reaches a high latency operation, be it a memory load, it will be swapped out, and the warp scheduler will actually dispatch and run another warp. If this guy is done, maybe potentially a third one, and so on is actually started. And then the whole thing goes again. So the mean to hide this latency is basically to exploit this pipelining or task parallelism, if you want to call it this way, okay? By swapping out active warps and in. So now this is all fine. And now you as a programmer come and say, let's go. This is so nice. And I found this beautiful picture, which is in the public domain. And this is how you should feel when you start programming for GPUs. There are a lot of, unmarked holes. I just love this. A sign for danger of unmarked holes. You shouldn't run, beware of deep shafts, and never walk backwards. And it's so fitting, I think, because it tends to be a hard business. So one thing to note, and first, is this whole concept to be kept in mind. GPUs are very much or very well suited to actually do a lot of computations. So you have to be careful that the algorithm that you might want to use on a GPU needs to overweigh compute over memory access. So for example, searching for a character in a string, I would not recommend this putting on a GPU, because it's just one if statement basically, and you basically will run into the memory latency one way or another, right? So for any application, arithmetic complexity needs to be high. So the number of arithmetic operations at best need to overweigh extensively, actually, the number of loads and stores. Then, coming back again to my beautiful picture of my workstation. So this is just a sketch of it. If you just look at the bandwidth, of the memory bandwidth, you might notice something that I tried to highlight in red. I don't know if you see it. So the access of the actual GPU cores to the memory is pretty darn good. Also, I took this from real experience. It depends on your architecture. Also, the access of your CPU to the RAM is also pretty darn good. But then comes the PCI Express bus, right? And this is, I mean, that's quite a factor. That's almost a factor of 5, and we don't want to talk about this difference, right? So keep your data where it is as long as possible, especially if it needs to go onto the GPU. Another thing which bites many people that just start is memory access on the device. So I just took 4 threads within a warp. Let's imagine that you just program away and you have a program that randomly accesses memory. And I really mean random. So our thread 0 accesses the first cache line. Our thread 1 goes to maybe the last one, wherever, 2 to the second, and so forth. This is a pretty bad setup, right? Because the memory controller, what it will have to do is replay for each thread access to the memory, it will have to replay the entire warp, okay? Which means that you execute your warp 31 times more than it needs to be, okay? And what you should have done in the first place in this, assign each thread for example, one floating point number in memory, which is close to each other. Okay, this is called coalesced memory access. So this is something to be aware of. Okay, so the summary, wrapping up this architecture part, GPUs are really complicated beasts. I mean, there's no question about this. But they offer massive parallel compute power. And I didn't talk about any discussion on exascale and energy efficiency and everything, but believe me, their performance per watt is pretty good. But you as a programmer, if you really want to suck out performance, you have to be aware that there's massive ways to kill your performance, okay? Which doesn't mean it's impossible. But on the other hand, I mean, at some point you have to take a step back and say, okay, I'm just a simple programmer, and here in this community we are all C++ programmers. So what paradigms are out there which actually suit my style of programming and are efficient, right? So I thought I'll take this metaphor of going into an instrument shop and trying to buy a guitar. So I don't know who has ever tried this as an amateur guitar player. If you go into a shop, you'll see something like this. And of course, the shop clerk goes to you and says, what do you want? And I don't know, because I'm just starting. In any case, so this is pretty much the situation I imagine you could be in. And I took this metaphor then to basically wrap up each individual programming paradigm and give a message to you what I think is usable or not. A word of warning, I hope you recognize this already. The smallest unit of concurrency on a GPU is 32 threads. That's an awesome situation. And on top of this, I think there are good tools out there, but rarely they are portable. So I would advise you not to start programming a GPU right away, but check if there is a good library out there that actually suits your needs. And there's a lot. So I just compiled, I mean, this is a highly subjective list. If you don't find your most beloved library, don't blame me. Open a ticket. I can add it if you wish. But this is just, you know, a selection. So there are a couple of vendor-specific or vendor-sponsored libraries over on the left. There are a couple other open source endeavors, multi-purpose ones. Last year, the author of XCL was actually around at this conference. Image processing, machine learning, which is a pretty big deal in the GPU business today, and bioinformatics, et cetera, et cetera. So, I mean, first, use Google or any other search engine and see if your field that you have to work on actually has a GPU library to offer. So what I'm going to use throughout the talk is the vector sum example, which is like a hello world in the HPC community. I'm using this one. People call it this ominous and really misnomed version of SaxPy. Just so I don't like this name, but anyway. So it's a very simple one. In my case, I take one vector A and another vector B and compute basically element-wise the scaled sum of A and B. Pretty easy. And inside the repository of my talk, I basically have a code directory where you can go and have a look at how it looks like for a real program for different paradigms. So let's start with CUDA. CUDA is, is an abbreviation for the Compute Unified Device Architecture that basically NVIDIA offers. It's a freeware, it's actually a lot. Let's start with, it's a freeware tool suite, it's a GPU library package, it's also a low and high level API, and it's also somewhat a compiler. This was actually the phrase that got me started in CUDA, because NVIDIA said CUDA platform supports C and C++, and I was like, yay, my favorite language, there it is, with a proprietary compiler. And the notion is that the binaries that you compile can only run on NVIDIA hardware, okay. One thing to note right up front, your source code will be split up, even though it resides maybe in the same source code file. There will be a host section, which currently in which the compiler supports C++11 and the standard library, and there will be the fun section. No, it's called the device section, which only supports a really, really tiny setup of C++11. And here this was actually my first disappointment, but we'll talk about this in a minute. So, going back to 2012, also when I started, there was a nice blog post on the Parallel for All blog by the NVIDIA developers, and it was titled 5 Simple Steps in CUDA. Okay? And these are the 5 simple steps to get a program running, in our case, the vector sum. So first you have to declare and allocate the host and device memory. Second of all, initialize the host data. Third of all, transfer the data from the host to the device. Fourth of all, execute one or more kernels. And fifth of all, transfer the results back. Just a feeling of you guys, does this feel like C++? Nah, not really. Let's have a look. So the top part, I'm basically going through this real small program. Let's use a standard vector. We stay with single precision, doesn't matter. Then we have to initialize 2 pointers that actually point to memory, or will point to memory on device. And then we have to use the CUDA malloc function to actually allocate memory on the device. And then we have to use the CUDA memcopy function to actually transfer the memory onto the device. Note, I actually skipped all the error handling fun, you know. Forget about exceptions. There's a lot of error codes that will be reported by these functions. I just dropped this, okay? So let's go on. You have to see the split. The actual program I started continues here. This is a kernel dispatchment. This goes after the paradigm of a grid dispatched kernel, because what I explained to you earlier, this whole grid and block notion, goes into this here, this strange construct that you have a function name, then comes these smaller than symbols, and then you define your grid, depending on the input data side, and the actual block size in number of threads and in number of blocks. So you have to do that. And then the actual parameters of the device kernel. And there at the top, there's your kernel. There's no pointer, but I could use the mouse. So this is actually telling the compiler, hey, this function is actually will be used on the host, because it will be called from the host and on the device. So it's called global. And there are your parameters. And first of all, what you have to do is use these constructs which just fall from heaven. They're available by the CUDA runtime. Okay? So you first have to calculate where am I? Okay? And then potentially you want to do some boundary check and actually execute the work. Okay? So this is what it's all about in terms of CUDA. And then what you have to finish with, copy the memory back to the host, and then be a good programmer and clean up after you. Okay? That's CUDA. So what do I think about it? Well, first of all, CUDA is free and it's working. That's good, okay, that it's working. CUDA itself comes with a ton of tools. NVIDIA did a really great job to actually provide you with a free debugger, very good, with a free profiler, and a lot of free libraries which come with the CUDA package. And also something very nice, it comes with a ton of examples. I mean, here you really see how much man hours actually went into this baby. So this is really a nice point to get started. It's still very flexible because besides the code, the very simple code that I showed you, it offers device intrinsics, so you can actually use special instructions to really exploit the hardware. Locked or pinned memory handling to accelerate the transfers from host to device. And one should really say that NVIDIA does a perfect job on being active in the scientific community, also in the industrial community, to porting applications. So if you have a big community and a lot of users actually want to urge you to go onto GPUs, I mean, I would actually just recommend contact NVIDIA and ask them if they could help you. And then also NVIDIA is very active in the C++ standardization. Now, if there's a green, there's also a red. CUDA itself is, for me, just a plain C API, okay? And this also holds for all the libraries. From a commercial point of view, in terms of budget, totally clear why this is, right? If you have it working once and C++ sucks it up, there you go. Problem is, your code will be cluttered with it. And there's a lot of software engineering pressure enforced on your library or whatever you are programming to actually follow this paradigm. For me as a C++ programmer, this is a problem, okay? This whole grid dispatchment, where you saw the greater than, and then you have to do all this kind of stuff, very error prone. Because the implications, you can do a lot of things wrong there. Because it has direct implications on how you utilize the GPU. And I told you in the beginning, this baby is four grand, right? And I personally, I think I would rather try to exploit it to the maximum if I can. The compiler NBCC is great, but it's sometimes hard to come by, especially if you want to do something standard in the C++ community like Boost, right? But I mean, don't let this be a show killer. Try it anyway. And what was also a big thing is the keyword thing. So this __ global, which I showed you, it's pretty disruptive in terms of design, okay? So this is just my experience. You might have others. Coming back to my guitars, I think CUDA is like a really good acoustic guitar. You know, you will start with it. You can play a lot of it, but it's not electronic or something. You can play a concert with it. You can be really good with it, but that's about it. Okay, in terms, so this is my C++ perspective, okay? Let's go on, OpenCL. Open Compute Language, sorry, no logo. I was so confused with licensing, I didn't want to put it in. It's open, royalty-free standards for cross-platform parallel programming. That sounds awesome. It's designed for a whole lot of architectures, CPUs, GPUs, FPGAs, and DSPs. The standard itself is maintained by the Kronos Group, a non-profit consortium. And very similar to the CUDA approach, the source code is split into a host and device part. Okay. Right now, the host API is very much lower level than CUDA, so you have a lot more things to initialize, to use, and to watch out for. And the device API is C11, basically. So this holds for OpenCL 2. For those of you who actually work with OpenCL, I know OpenCL 2.1 would support C++ 14 on device, but I wouldn't want to put it in here because there's simply no compiler out there, as far as I know. If I'm wrong, I'm happy to adapt. Okay, this is how it looks like. I just pasted in the kernel for our vector edition. You basically see that it looks very similar. You again have this notion of the __ keywords. Then you have a function signature. Again, this global returns, and then they have a little better API on device. So this whole ID computation, you can actually, the API does for you, but the rest really looks the same, right? Oh, actually, there's a typo. That should be out. My scale, I forgot my scale. Anyway, one thing to note, I said portability. What you might have discovered when I flashed the slide, this is a string. Right? So there are two modes of compilation, and hopefully this will come to an end soon with the SPIR 5 intermediate representation. And this is a string that at runtime will be compiled. So it better be correct. For me, a no-go, to be honest. As a developer, no go. There's also another way of compilation. You can also compile it directly, but then you are stuck to the hardware that is actually found on the actual host where you compile, as far as I understood. Sorry, not my thing. So for me, OpenCL is like a harp guitar. You know, it's one that it has a lot of strings to pull. And I mean, it's certainly possible to get music out of this, and many people use it. For me, CUDA is already a little bit too complex, to be honest. So it depends on your use case and probably also on your taste. So now let's get a little bit going with C++ on GPUs. There's Thrust. Thrust is a NVIDIA-sponsored C++ template library, which comes with a CUDA distribution. There's a similar project for OpenCL called Bolt. It's open source. You could look it up on GitHub. It's interoperable with CUDA, Intel threading building blocks, and OpenMP. So these are the three backends that you can use. And it's basically, it has a much higher interface or high-level interface than CUDA itself. So let's have a look at it. First, as good C++ programmers, what do? We write a functor. That's just how we work. So this is the functor actually that needs to be executed on device. You see down here our vector sum. So, I mean, this is pretty much syntax that probably most of you will be familiar with. Thrust offers an API to actually inherit from, so that the internal runtime system actually can take this easily, this functor. That's just some boilerplate code, which reflects the fact that I need to hand over a parameter called A, and this is the actual code to be executed on the device. Okay? So how does the host code look like that you actually use to run this? So first of all, see the namespace. We're not anymore in standard. We are in Thrust namespace. We allocate a host vector of some size. Then we do a copy assignment or copy construction into a device vector. This is where actually, as far as I know, the transfer of the memory is triggered. And then we have, similar to the STL, we have an algorithm API where we just hand in iterators and the actual functor. So this, I mean, this now feels like C++, right? Composability, separation of concern, the whole memory issue is put out into this container API, and the actual algorithm that actually does the heavy lifting is inside the algorithms. So what do I think about it? So C++ and the STL for GPUs, that's good. And it's actually even working for CPUs, although I didn't use it yet for them. I like the separation of container and algorithm because it feels natural for me as a C++ programmer. The code becomes readable, I think. You still have to know what's going on, of course, but it becomes more readable. The algorithms itself, something I didn't mention, can also be dispatched from the functor, so on the device. That's also something very nice if I actually want to use dynamic parallelism. And there's also seem to be an active community and many examples. So if you want to get started, I mean, that's the GitHub repository is the way to go. Problem for me as an HPC guy, we lose flexibility, right? This whole host device input-output, so the whole transfer, is now put into the API, into this vector API, which is good, I said, but it becomes a little bit intractable. For example, that I need something I need a lot, which is this pinned memory allocation, so I can accelerate transfers, is still experimental. So this is something when a library by a vendor says it's experimental, I go, maybe I should be careful. The index information, so where am I for complex kernels, is actually lost, or only available as far as I could see through kernel build-ins. And the whole grid dispatchment is done by the algorithms, which is good for one thing, for beginners especially. On the other hand, if I know what I'm doing, maybe that's not so good. If I have compute-heavy kernels, then the only way to do optimizations on device is again by providing functors which relate to the CUDA API. And for me, what I found a little bit irritating is, what about C++ and C++ 11 and 17 support? I couldn't find anything in the Trust documentation. It looked to me as if this would still be a C++ 2003 library, which is fine, but I just didn't find anything. So what's Trust like? I think it's like an electronic bass guitar. So it's electronic, so it's like, whoa, 21st century. But I mean, you know, the bass guitar is just there for giving you the rhythm. It will not play a melody, right? So with this, I want to convey, so you lose a little bit flexibility and you still get the job done. I mean, you can play music, but you have your restrictions, which is maybe not something I want. And now come to a new project sponsored by AMD, which comes from APUs. Nobody get the joke? Apu from The Simpsons, anyway. So this project actually was motivated by accelerated processing units. You know, these shared architectures by AMD, where actually the CPU shares memory with an on-die GPU part, and they actually share the same address space. So they came out with a Clang-based or LLVM-based compiler, which is called HCCC. You can reach it through this URL. The promise here is that it's a single source C++ compiler. So for CPU, GPU, and APU targets, again, it supports a whole lot of standards, C++ AMP and HC. So I will talk about this in a minute. OpenMP4 and C++ 14, I think, and 17 potentially. It's currently ported to discrete GPUs, something I work with mostly. So the idea behind originally was, okay, let's put something out for APUs. And now AMD has decided to go forward and actually extend capabilities to discrete GPUs. And I really have to say, I was debating with myself if I should take it into this today section or the tomorrow section. At the end, I thought, well, the compiler is usable as well, on Linux as well. So why not just take it? And it was presented to the standards just recently. So this is how the code looks like. So again, we have our sum function. This is all host code. Okay. So we can still work with our standard vectors. First difference, we have to define the extension of our arrays, which is a nice construct, as we will see later on. And something very nice for me as a library vendor or programmer, they offer views. So I don't have to copy anything per se when I get a pointer. I can say, well, this is a very thin abstraction on top of a given vector, for example. And I can tell it, well, I will get an array. Don't copy it. Just leave it where it is. It has this extension, and it comes from this object, or this reference in this case. So that's a pretty nice step forward. And I can actually tell it, well, it's a read-only array. So I provide the const keyword. So this is pretty nice. And if you look at the actual work to be done, it looks, for me, very much more C++. So there is an algorithm called parallel for each. I provided an extent because I have to define what portion of the memory, how it's structured. It's supposed to work on. There comes a lambda. This is taken from actual working code. AMD developers told me they want to get rid of this restrict, which I'm very much in favor of. So you provide a lambda with a defined index object. So this basically communicates with the extent. And then I can simply use the index as I know it in the scope operator and then do my work. And then I'm done. Nice thing as well, the API offers manual synchronization. So I have control over which portion of memory is transferred where. Okay? What's good about this? So the API focuses on problem solving, I think, in a C++ way. It appears to be lightweight. As I showed you, these arrow views look very tempting for me. They want to provide many or some binary backends. Currently, they are supporting OpenCL, and as soon as good drivers are out, SPIL 5 will be supported. They support multiple hardware backends. It's a homogeneous C++ code, given the fact that this restrict statement will go away. And they also will support function continuations, which I will come to back later. And this they support right now. Red part, it's a very young project. Okay, what they will do, as far as understood, they want to basically move entire capabilities of the concurrency namespace, which is very much based on C++ AMP 1.2, into this HC namespace. So there's still a lot of work to be foreseen. There's no tooling yet. This is something for me as a developer, which is a problem. At least I haven't found any tooling. The performance yield is pretty much unclear. Unfortunately, I didn't have time to actually do some performance measurements, which are possible by the API, but I just didn't have the time. The combined API for integrated and discrete GPUs I see as a problem because of the architectural differences. On an integrated GPU, I don't care about memory transfers. I simply don't. And that's one of the reasons why I see this as problematic. So let's see how the API evolves. And this is my personal feeling, so forgive me for this. The HSA, so the collaboration for the APUs and AMD's roadmap is pretty much unclear to me. So, I mean, there are good products out there in terms of performance per dollar, but I simply don't know how it's going to evolve in terms of HPC. What's HC like? It's like these 1932 electric guitar. So it's modern, you know. You can play the melody voice with it. It looks strange. And you don't really know how is this going to work out, like on a massive scale. So yeah, so this is my metaphor. And then last part of the today part, or what you can use today, is the PRAGMA-based approaches. First of all, OpenMP version 4 that started to support the target keyword, meaning that they also now support calculating on accelerated devices. And this is how it looks. So you first again have your vector sum API. Here is the for loop that you know, and then you spice up your code with some PRAGMA statements and be done with it. There is an alternative project called OpenACC, funded mostly or in part of by NVIDIA. So it's basically the same approach. You have your API, you spice it up with PRAGMA statements, and you can keep the code as you know it with simple for loops. What do I think about it in practice? Well, I mean, there's no question about it. OpenMP is a success story on a CPU, right? I mean, many people use it. There are pitfalls, there are problems with implementations, but I mean, people use it full stop. The dream connected to this approach is you just inject one line in your code, and then it will be fast. And everybody smiles. World's good, done. It has a very strong industrial support, which I like, especially from an open source perspective. And I would say that these PRAGMA approaches are perfect fit for upgrading legacy code, so it's code that you don't want to touch actually. You say, yeah, it's doing its job, but we know it has its deficiency, so let's just give it a shot. Or for prototyping. What I don't like. I think OpenMP has left its mark on CPU multithreading. I do not think that it will really fly on discrete GPUs, simply because of the architecture. Because what I will do now, I will insert a PRAGMA statement that will do something with my memory. And it will ignore if it's a slow memory connection, I'm on an old machine, PCI Express 2, you name it, or will it be a new machine with very brand new, let's say, NVLink. As a developer and software engineer, language in a language is a no-go for me. I mean, it's very capable, it's very flexible, given, but it's a language in a language. No. OpenACC and OpenMP, I really don't get what I should use. I'm sorry, I hope that people that watch it on YouTube actually maybe will get in touch with me. Because there are good compilers for both. It works for both. So what should I do? People say, yeah, this is more an experimental ground. Other people say, no, use it. It's the way to go forward. I don't know. What is it for me in terms of discrete GPUs? It's like a ukulele, you know? I mean, you can learn it fast, and you can certainly play wonderful music with it, but it will stay a ukulele, okay? And I don't, yeah, that's what I think. What can you use tomorrow? I found this picture interesting, an electric guitar with a touch screen. All right. Woo. Okay. Don't want to have wet fingers there. Anyway, a project that came to mind, so there are a couple of projects. I forgot a couple. If I did, feel free in the questions section to stand up and tell me. First thing, Boost Compute. because this comes from Boost. It's not a part of the Boost library. Their goal is basically to provide a C++ SDL-like OpenCL wrapper, enabling vendor-independent parallel computing, basically based on the idea of OpenCL. Conceptually, it is very, very simple to thrust and bolt, if you look at it. So here's basically the API that you would use. So they adopted the notion of device objects that you have to initialize, context objects that you have to hand over which device you want to run on, and the command queues. But they did it, I think, in a very cunning way. You can basically stay with the API of a standard vector, only that you have to exchange the namespace. It's very similar to thrust. You basically, once you instantiate this, as far as I understood, this is basically telling the system, okay, this needs to be able on the device. You can do manual copies. And for this looks very similar to the standard copy, only that you have to provide the queue. So this is basically a heritage from OpenCL. And then you can do very similar to the standard, do the algorithm that you would like to. What's from the OpenCL community as a broad, or from the Kronos group, what's the roadmap there? Well, I wanted to show this very recent slide because there's a lot going on. I personally, it's quite a lot, it's amazing, but I want to see what compiler actually will support, okay? Because I'm a developer. So you see a couple of things here, C++ AMP, I introduced this somewhat. SYCL, a very new development, very interesting, looks from the API very similar to thrust and bolt, but of course, as it's basically motivated inside the Kronos group, if I remember, they want to go for compiler support. And there's OpenACC as well, besides other projects. So the takeaway here is basically that all of this will, I hope, fly even more once support for binary intermediate representation is out. As I said, especially SYCL is very, very much like thrust and bolt. What about CUDA? What is their roadmap? So I brought two snippets on the way forward. This is something that was shown at GDC, the NVIDIA conference earlier in the year. So if you want to stay, well, my arm is too short. With the vector sum example, they want to go away from, or the idea was to go away from this whole grid dispatchment and rather just provide a launch function which you hand over your function and its parameters, and the API does the grid dispatchment for you. And something that was already said yesterday in Michael Wong's talk and also at the HPX talk, this is executors basically. And so the idea is here that you still have some API to do some bulk asynchronous dispatchment. You have a policy, if I understood correctly, that actually does the chunking over your input extents or shapes. And then you still have a lambda function that defines the work to be done on device. But there is actually an executor, if I understood correctly, or maybe it's this one. I wasn't so clear about this. And here's the work to be done. And the nice thing is that you can actually marry this with continuations, which I think is an awesome thing to go forward. But let's see how early this will be available. C++ 17, I have to hurry up a little bit. Basically, they will offer in the parallelism TS something that you might have seen already. Basically, you hand in over a policy, how you want to parallelize this, our iterator ranges, and then again a lambda for doing the heavy lifting. And the notion here is that many vendors have actually promised that inside their compilers, they will actually offer individual targets for CUDA devices, for OpenCL devices, etc., etc. So let's see. But actually, I'm not too excited about this, what I just showed you from the parallel TS, because again, it ignores the notion of discrete GPUs. I'm again subject or victim of an automatic mechanism to do the transfer, right? Which I don't want. I want to control it. So my personal excitement with C++ 17 is this. Concurrency. Yay! Because it finally allows me to actually have a nice API to asynchronously organize my transfers from host to device. So here with these function or future continuations, first I define a future to copy my stuff onto the device. Then I tell it, okay, after this is done, please do this, how we work, whatever. And after this is done, maybe you want to do the copy back. And this is actually something which I'm very much looking forward to, because it allows me in a C++ way to express the concurrency that I have to do simply because of the architecture. There's no way around it, okay? And there are other concepts which I'm very much looking forward to, the await and then, which was basically shown last year by Roland Kaiser in his keynote. These are all constructs which me as a GPU developer, I'm very much looking forward to. Again, if you're working on a shared architecture, so GPU and CPU are one thing, this is probably, you don't care about this. Okay, it's just because of the discrete nature. And I come to my summary. C++ on GPU is done right. Well, to be honest, today, in production, there is no C++ on device and on GPU. That's as honest as I can be. On the horizon, there are very performant and flexible and maintainable C++ APIs emerging, and I'm very much looking forward to this. Still, if you want to start today, you will go to this shop and have to decide on your own, okay? I just gave you the ability to judge. And something that we cannot ignore, GPUs are here to stay. I mean, they make workstations into supercomputers and clusters into supercomputers as well. It's complex. Obtaining maximum performance is challenging. It's not impossible. It's a great fun work to do. Accelerators are a must to the road to exascale. And with this, I would like to briefly flash my acknowledgements, my colleagues from the company that hired me, Psionics Computer Innovations GmbH, and at the MPI CPG. And we also have interest in a GPU Center of Excellence and by NVIDIA and AMD. And with this, I thank you for your attention. And I encourage you to go onto the GitHub page. And if you have any problems, compliments, comments, critique, just go ahead, open an issue, and I will reply. Thank you. Three minutes to go, if I see correctly. Michael, sure.
Thank you for that summary. I think it's great. People can see all the different advantages and disadvantages. I think I totally agree with everything you say there.
I appreciate
I'm hoping I'm not one to make predictions, but I seem to do a lot of them because that's part of my job now.
Yeah.
I'm hoping that we will be able to get a GPU-capable C++ in about 3 or 4 years in the standard C++20. I think my subgroup SG14 is going to do the best it can.
Thank you.
To deliver something that is extremely C++ friendly, that leverages lambda expressions and, as you said, futures continuations as well as all of them parallelism TS.
Yeah, thank you for that work.
Well, I might have one. From a very practical, there's actually two things. From a very practical perspective,
thank you. We've done work on FPGAs for HPC, and from a very practical perspective, we found granularity is a big issue.
Yes.
That you just mentioned the 12 gigabytes, and
that
was it. Number two. Much of this is bare metal. I mean, CUDA is bare metal, which is great. Thrust, I wanted to ask you about your experience when you used Thrust, about falling back on CUDA. Have you done that?
No, I haven't done that yet.
Okay, because that would kind of give you back the bare metal. So
I mentioned it. I mean, on device, you certainly
because,
can do
much
that.
of the rest to me at this stage is wishful thinking.
Yes, I agree. I have to agree. Good.
So I'm not a GPU developer at all, but I'm just interested. You said a lot about like the C++ API on the host side and like how to dispatch these jobs. How much C++ could I use actually in the kernel? Could I call other algorithm STL functions inside the kernel, and what would happen then?
No. Okay, so maybe I was a little bit too blunt here. Let's stay with CUDA for a minute, because this is, I think, the more widespread paradigm. So on the kernel, in kernel space, you basically can use, let me think, auto, lambdas, template programming. That's it. So the rest is boilerplate, as you just said. So I hope that this will change. And certainly you can call other functions from kernel space, but I cannot say more than this.